Hey everybody, it's Norm from Tested, and I'm so excited to introduce you guys to this guy right here. It's Kishore Hari. He's the director of the Bay Area Science Festival. Now, I'm not interviewing Kishore because we're going to be interviewing some people together.
We have an amazing lineup of people we're talking to about robots.
Robots, biorobots. Now, we're here at the Swiss Next Institute. They bring organizations and researchers from Switzerland, and tonight we're speaking to people from the EPFL.
EPFL, one of the major science institutes in Switzerland, and we have a special biomimicry robotics group that came over that model all sorts of behavior of snakes and fish and salamanders and reptiles, all to understand how biology from nature can really inspire the next generation of robotics.
Biorobots, lovable or creepy? Let's find out.
Hi, I'm here with Auke Ispeert, and to talk about these wonderful biomimicry robots you have. Who do we have on display here?
So this is Amphibot. It's an eel-like or lamprey-like robot.
So remind us, what is a lamprey versus an eel?
Yeah, so lamprey is a very primitive vertebrate. It's one of the oldest vertebrates existing, so it's still a fish. Eel is a bit more advanced. Both are fishes, but they both share exactly the same type of swimming.
It's that basic sort of undulation through the water?
Absolutely. It's called anguilliform. You have a nice traveling wave ondulation propagated from head to tail.
And why did you want to study a lamprey motion? You said it's one of the most ancient animals. What can we learn from something like that?
Yeah, there are two main purposes. The first one is for neuroscience. It's like a tool for neuroscience to understand the spinal cord of the real lamprey, because it's probably the animal of which we know best the spinal cord. So we use it as a test bed, basically, to test hypotheses of how it's organized.
Meaning that a lot of neuroscientists have been studying that lamprey for a long time, especially the spinal column?
Absolutely.
Does it have like a brain, like how we associate brains in other animals, or is a lot of this controlled through the spinal column?
Well, that's the interesting part. It has, like any vertebrate, a upper part of the brain, and it has a spinal cord. But for locomotion, it's really the spinal cord which is the key element. And people know it, like you can cut the head of a chicken, can still run for a while, because the spinal cord is really the controller for locomotion.
And even though it's simple motion, how complex of a creation is this robot?
Well, the big challenge was to make it waterproof. There we suffered a bit. So we had some generation to make it really waterproof. Otherwise, what's nice, it's a very modular design. So we have little elements. Every module has its own microcontroller, battery, and it has a CAN bus to connect them. So we can very easily make the robot longer, shorter, or even add legs. Later on, we'll see a salamander version of this robot.
And how long are lampreys usually?
So a lamprey, an adult is like 1 meter.
1 meter.
1 yard, yeah.
And when you are testing this robot, are you looking at that specific 1 meter length, or are you looking at even longer lengths or even shorter lengths to model this kind of S-wave pattern?
For us, because as you'll see, we have some kind of granularity problem, like the fact that the modules cannot be too small. It's good to be at least 1 meter, otherwise you cannot really propagate properly the traveling wave.
And how long can this thing go in the water?
How long it can swim? Yeah, probably for half an hour non-stop easily. Possibly if you have a few stops for 1 or 2 hours.
And so tell us about the intelligence in this. Like, it's one thing for this to swim through. We've all seen those toys that swim through the water that are just going through the same motion. What are we seeing inside here in terms of the intelligence? Yeah,
the intelligence is really this kind of replica of the spinal cord circuits. And what's nice, it's a very distributed system. So you can almost cut it in half, and subparts of the spinal cord can still work. And not the animal though, the animal would die. It's not like an invertebrate, like a leech, but the lamprey would die, but you can really, it's a very distributed controller, let's say. And what's interesting, it's very robust. So you can really modulate it, disturb it a lot. And what's maybe the most fascinating is the signals coming from the upper part of the brain being sent to the spinal cord are very simple. Just 2 signals. You increase both of them, you go faster, you stimulate more one side, and you'll turn towards that side. So you'll see a demo when it swims, it's very easy. It's as if you had a remote control car, like just 2 signals to control the whole locomotion. And I think that's nice, because that means the upper part of the brain doesn't need to worry about muscles, what every muscle should do. It's really the job of the spinal cord to do that. And the upper part of the brain will just do high-level modulation.
And so this controller basically has what you said, just those 2 degrees of motion.
Absolutely. So Alessandro Crespi here, the postdoc in the lab who developed the electronics of the robot, is basically playing the part of the upper brain, let's say. And then he sends these very simple signals to the spinal cord model, and that's running in real time now with little mathematical models on board of the robot.
How complicated a mathematical model is it to mimic this behavior?
It's fairly simple. Like the complexity comes from coupling the oscillators together. So it's a network of coupled oscillators from a mathematical point of view.
What does a next generation of this look like?
So we have a new version which is longer, more rugged like for field, like a field robot. So we use it for pollution detection. So we have a GPS on board. We can do navigation.
So it would be autonomous. It can
Absolutely.
we can unleash a number of these throughout a water system.
Yeah, you can give waypoints. It will go to the waypoints, or more interestingly, it should be able to find the gradient, like climbing where the pollution comes from.
And even that sensing equipment, I mean, we've seen GPS get that small, but the actual chemical detection can be miniaturized into something this small?
Yeah, that we have colleagues in Lausanne that work exactly on that. So that's not our job, it's their job, but they do a very good job for some of the sensors to have them on board, absolutely.
Oh, this is a cute little guy.
Yeah.
I have a little fondness for him. Do you have a fondness for the animals?
Yeah, absolutely. You know what? This is one of still my favorite robots that we have in the lab. And one of the reasons is that if you take it out, the appearance looks like nothing. It's just a set of boxes connected together. But what makes it cool is the motion. It's the motion that makes it lifelike. So easily we could make a skin over it to improve the appearance, but I like this notion that the appearance is not so beautiful, but the motion is beautiful.
Thank you for showing us the Lamprey.
You're most welcome.
And so from water-based systems, we move to land-based systems, where locomotion is a little bit different, but snakes. We have land. So this is Camilo, and tell us about your snakes.
Okay, well, these snakes are a robot that are very simple, let's say, in the way they're constructed. For example, we have one motor that have only 1 degree of freedom. Then we just twist the motor to have another degree of freedom like this, and then we just continue with the same chain, doing all over the number of models that you want to put.
Now, in terms of biomimicry, you're trying to mimic the versatility and the motion of a snake. A snake doesn't actually have just 1 degree in turn, or does it?
No, it doesn't. I mean, depend on what gait you try to reproduce. For example, you can see that actually the body moves like a real snake, right?
Yes.
And we have also this vertical plane, so you can move it in many directions. So depending on the gait you're trying to do, for example, side-winding snakes, you can just reproduce it the same way as the real snakes does.
When you study a land snake, right, and its gaits, it can slither forward, like you say, it can move sideways, it can coil. Which are the motions that you find most interesting for this type of robot?
Yeah, there is one motion that is quite interesting, is this one. You can see, this is called rolling. So basically what we are doing is just try to maintain this arc shape all the time, but the robots are moving all the time like this. So every model just move like this, but as you can see, you combine this motion and you have a rolling. So that's very interesting because, for example, you can wrap around something like a pole, like a tree branch, for example, and then you just roll and you can just progress with this motion.
So it's how it's traversing along other long objects, basically.
Correct.
Some type of a pole or a girder.
Or even the ground.
Or on the ground.
You can have a little bump, but you can still pass over it.
Right, and so when you're designing something like this, it's not just to illustrate how you can use engineering mechanics to mimic the biology of an animal, but there's also practical application.
Yeah.
It's not just making robot snakes for robot snakes that tie around Kishore's neck.
It is. But the practical application that we most envision is, for example, going to a search and rescue mission, right? So, we have this cross-sectional. So basically this is super slim, so you can put it through any borehole that you can imagine, like this size, and then you can just, once inside, you can just move and do a lot of things, right? So as I mentioned, we can have different types of gait, so it doesn't matter how the terrain is, how it looks, you can still try to go in this gait and then just change to another one. So this is what we call multimodal locomotion. So this is pretty, let's say, convenient for this kind of scenarios.
And I imagine putting a camera on a robot like this is very useful for search and rescue. Now, how does this scale? Can you add more links to it and make it a longer snake? Does that change how it moves?
Yeah, of course. For example, I'm going to show you something. We have here 8 degrees of freedom. That means 8 modules. It's quite a small snake, but still we can do a lot of things. This big one over here, it has 14. This one is 16, and this one here has 24.
24. Wow.
So you can see that we can scale. The only, let's say, drawback is that as you scale the size, you need more battery power.
Yes.
So in that case, you need to put, for example, in the head, we have this controller in one end, and in the other one we have the battery. So if you scale it even more, you need a large room, let's say, for the battery.
But the software also scales appropriately?
Software is exactly the same.
It doesn't get more complicated, it doesn't
Not at all.
tie itself
it's
up?
quite simple because basically you just control 2 waves, one vertical and one horizontal wave, and that's it.
That's amazing.
Yep.
Well, the snakes don't have legs, but we're going to take a look at robots that do. But thank you so much for sharing with us the snake robots.
You want to hold it?
Absolutely. Woo!
From snakes to mammals.
Oh yeah.
What do we have here?
So this is a little Cheetah Cub. It's a bio-inspired robot modeled after the animal, a cat or a dog, so quadrupedal mammal, terrestrial mammal. The cool thing about this robot are actually its legs. So you have here these 3 segments, 1, 2, 3,
And this string kind of
with the
connecting.
string connected, exactly. So one motor that's sitting here, that's doing the front and back movement, and one motor that is compressing the leg. So for that I have to hold it here a little bit, like compressing here the leg, and the spring is extending.
How much is that like how our arm moves?
Actually quite similar, because you have this antagonistic motion, so you have always one muscle that is contracting and one muscle that is protracting, and exactly that's what the motor does. The motor is contracting and the spring is retracting again.
This seems like a very robust system. How fast can a creature like this move? With what is like, seemingly simple two motion system.
Yeah, that is actually the forte of this robot. It goes up to 7 body lengths per second.
7 body lengths per second. So
yeah.
let's translate that into some metric units.
It's a metric unit. Metric unit is good. So that's 1.4 meters per second.
Oh, that's pretty fast.
Yeah, that's about.
I can't outround that by much.
Yeah, that's about like a human would fast walk. Yeah. So that's the maximum that it can go.
That's pretty. That's exceptional, just with this simple gear system,
and especially because it has no sensors on it. So this one is completely open loop, doesn't know about the environment, and these intelligent mechanics, they're actually stabilizing the motion.
So what happens when we start to add sensors to it? What does it start to look like?
Then it starts to look much like this one here. So this is on Chile. They have a lot more. It's a lot bigger, a lot heavier.
I see you've added socks.
Yeah, yeah, we added socks for aesthetics. No, but that's actually for protecting 3D force sensors that we have in the feet. So this is 3D contact sensors in the feet. We have encoders on each joint of the whole thing. The legs are exactly the same principle. You have again the protraction, retraction, and the compression, decompression.
When you say there's force sensors in the feet, what is it really trying to sense? Like how stable the ground is below it, the shape?
Exactly. So you have a little bit the possibility to go into reflexes. So for example, a stumbling reflex. When the foot hits the obstacle and the robot would normally stumble, it retracts the leg even more, and like this moves over the obstacle. And that's something that we can sense with these sensors.
What kind of processor do you have to have inside of this to in real time monitor all these sensors?
Actually, not much. There's a 1 kilohertz, 1 gigahertz sensor on
1 gigahertz
processor on it. We're using CPG networks. They are very low. They have a very low computational cost. So, and to add sensory feedback doesn't cost much in computation, as long as it is feedback like this, another camera or something. Camera imaging costs a lot of computational power.
Can we see it actually move?
Yeah, we can. So let it run in the air a little bit, and then show the abduction if you can. Nope. Okay.
So it's starting to run a little bit in your hand.
In my hand.
What does that feel like on your hand? How much force is exerted? Is it hard to control?
You can feel it. I mean, you can feel kind of an inertia.
Yeah.
But the legs are actually very low
it's
inertia
very balanced,
in general. Yeah, it's balanced. The robot is mostly symmetric. So left, right, forward, back. It's quite symmetric. So it has a good stability due to this construction already.
So how fast does this guy go?
It's about 0.7 meters per second.
So it's similar to the previous one.
Yeah, half the maximum speed of the previous one. So
is that a limitation of the actual technology you're using, this sort of like pulley system, or is it the limitation of the battery or something else?
Let's say it's a little bit the limitation of the power that you can put into the motors, because we drive it on a battery, but also on the same time. It's a very safe and economic way to drive the robot. So at this speed, we get the most runtime out of the battery, let's say.
So why don't we let it on the floor and see it move around?
Here you go.
Oh, I had it backwards. I thought.
And on the cable.
So besides the 3D touch sensors in the feet, what other sensors are on board?
So there are encoders in each joint, backwards. Encoders in each joint. There's an IMU on it, which you can have a posture control with it. Sorry.
Is it stabilized or will it fall over?
It's quite stable from the mechanics already. So the springy leg, it's putting the robot in a very stable position in general.
What are the applications of building a cheetah like this? What are you really trying to model in terms of the locomotion?
So in the locomotion, it's very interesting because you can see how good the mechanics are already before the actual control kicks in. So you outsource a little bit of the control effort in the mechanics itself. And like this, you gain a lot of computation space, let's say, for higher computation tasks, like vision, when you would want to put vision on it, or something like that.
Thanks for sharing us the Cheetah Cub.
Yeah, thanks for talking to us about it. We're very excited.
And finally, robots that may not exactly be inspired by a real animal in nature, but something that maybe takes lessons from the previous robot. Simon, tell us about this Roomba, this modular robot you have.
Exactly, it's a modular robot. So this is one unit. It consists of two inseparable spheres that have 3 degrees of freedom that can continuously rotate, like this, and in those two diagonal directions. And then each of those modules has 10 attachment planes. And in some of them we have hooks, retractable claws that come out, like this.
Oh, wow.
And this enables one module to connect to other modules and form a bigger structure than one module itself.
But they are self-sufficient just in this pairing.
Exactly. Everything is in here. We have battery in here. We have all the sensors for our motors in here. And we have communication over Bluetooth to our centralized PC here.
Now, locomotion is a theme that we've gone through. We saw from the Lamprey, basic locomotion in water, it's all the way to a quadruped. This one doesn't have legs, so I imagine it moves a little more like the snake robot we saw earlier.
So here's the cool thing about them. We can make them move like snakes, but we can also configure it into a different robot and make it move like a quadruped.
These can be legs.
It can be everything what you want them to be, yes. So this is, we connect them how we want them, we play our control, and we can make them move like an animal or like a snake or however you would like them to be.
Right, how they latch together, I imagine, is important because it needs to be strong structurally, how many points they can latch together. Now, how did you decide upon, one, you needing 2 units to be a singular module, and also the axes of movement?
So this is, just see it as a little more complex module than from the snakes. So we they had 1 degree of freedom. Now we have 3 degrees of freedom that allow them, each module by itself, to be a little more free than the others are. And I don't know, they look cool like this with diagonal degrees.
And it's an experimentation. You're figuring out what happens when you add 2 more degrees of movement, when you have the algorithms from the other animals that you can configure to make this wiggle, to make it crawl, to have them attached to each other. Now, how many have you actually put together?
So right now we are in the process of building more. The furthest we went was maybe 4 or 5 modules. We made the structure stronger, the gear stronger, so now we're hoping to put some more together, maybe 8 to 10, something like this. we are in the process of doing exactly this.
And in between actually building modules, it's just lots of simulations running?
Oh yeah, definitely, yeah. We have to make sure that in the simulation our modules don't collide with each other. If it will happen in the real robot, unfortunately they would immediately break. So we need to invest a lot of algorithmic simulations for this.
Do you and your team imagine that this is something that can be used not only in the field but also indoors and can be a part and miniaturized?
Definitely. So the name Roomba comes from the vision to have, instead of furniture, you just have a bunch of those in your room, and you configure all your furniture with those Roombots. So imagine you wake up in the morning in a bed out of Roombots. They configure into a chair, in tables. If you have more guests, you just take a bunch of those more, and they will configure into sofas into your living space. So this would be the future vision of things.
And you're taking lessons from real-world animals and movements and other animals and snakes and quadrupeds,
whatever we can,
and it's going to make a beautiful modular chair in the future. That's
exactly.
Awesome. Thank you so much, Simon,
You're welcome.
and your team at the EPFL. It's been great chatting with you guys, and we love your robots. Thank you. Kishore, that was awesome. Adorable, it turns out.
Incredibly adorable. I think I want to adopt one.
Yeah, the Lamprey. That's what I put in a bathtub.
Yeah, I loved the Lamprey, and I loved how simple that motion was, but how lifelike what it looked like and felt like. It was almost like I fell in love with it. It had emotions to it as it was swimming through the water. But what really caught my eye was the Cheetah Cub. It was just that simple motion, that sort of back and forth motion, how they could actually get, basically like normal walking speed out of a simple, what looked like a pulley system.
I remember those like Transformers toys I used to have, and they would have just the motors up here and kind of scuttle around.
It had that same sound too, from those old robots. But what's really
way more elegant
and beautiful, how the gait sort of slowly moved through. What about the self-assembling robots?
The self-assembling robot is kind of like the thing that's far out in the future, like a Futurama, Jetsons thing. They want to combine these modular robots, and they're big right now, but they can be smaller, and have them. You can group dozens of them together eventually, swarm them, and have them build chairs and furniture.
Well, I think the swarm of the self-assembling robots sounds a lot better to me than the swarm of snakes.
Right. Yeah, but you know what? They're all going to move like snakes. You got to go from 2 to a snake, then a chair, and then it's okay.
The progression of locomotion was incredible, so I can't wait to see more robotics in this biomimicry realm that allows us to use that sort of nature-inspired to do everything from climbing walls to maybe even flying. And we got to thank SwissNext for inviting us here, thank the EPFL and their researchers, and thank you, Kishore, for bringing us here as well and chatting with some of the researchers. We'll have more of Kishore on Tested. We're going to go to really interesting science institutes, meet more robots, talk to other researchers and scientists. A whole lot more science. And so stay tuned for that on tested.com. Until then, we'll see you guys next time. See ya. Bye.